Light crosses a room before the mind can register that it has begun moving. It circles Earth more than 7 times in a single second, travels from the moon to our eyes in little more than a heartbeat, and reaches us from the sun in roughly 8 minutes. Within the scale of human life, its speed appears almost infinite. A lamp is switched on and illumination seems to occupy the room at once. Lightning divides the sky long before thunder arrives. Every ordinary experience teaches us to think of light as the swiftest messenger nature could possibly provide. Then the universe reveals its true dimensions. The same light that crosses a continent in a fraction of a second needs years to reach the nearest star, tens of thousands of years to traverse the Milky Way, and millions of years to move between neighboring galaxies. Across the greatest observable distances, a beam may spend nearly the entire age of the universe in flight. The fastest thing permitted by physics becomes painfully slow when confronted with a cosmos whose distances exceed the reach of ordinary imagination. This creates a strange division between what exists and what can ever belong to the same moment. Stars may be visible long after they have changed. Civilizations could flourish while their first signals remain trapped between solar systems. Entire galaxies can pass beyond the range of messages sent today. The universe possesses countless regions separated by intervals so immense that even light cannot keep them meaningfully connected. Its speed governs causality, knowledge, travel, memory, and the borders of every possible future. Yet measured against the architecture of the cosmos, light seems almost motionless. The speed of light in vacuum is exactly 299,792,458 meters per second. Physics gives this value a special status because it reaches far beyond the behavior of visible light. Radio waves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays all move at this same speed through empty space. Gravitational waves also propagate at this limit. More deeply, this number describes the maximum speed at which information and causal influence can travel through space-time. It forms part of the structure of reality rather than merely measuring the performance of a particular kind of particle. On human scales, the number is overwhelming. Light could travel from Paris to New York dozens of times during the blink of an eye. It could cross Earth from one side to the other in less than a 20th of a second. A signal sent to a spacecraft orbiting the moon requires only around 1¼ seconds to arrive. These delays are short enough to feel manageable, though even the lunar distance prevents a perfectly natural conversation. Every question must cross the void, and every answer must make the journey back. A pause of several seconds enters each exchange, generated by space itself. Our intuition evolved within environments where this limit rarely becomes visible. Sound, animals, storms, falling objects, and human bodies move at speeds so much lower that light appears instantaneous. The nervous system cannot distinguish between a lamp illuminating a nearby wall immediately and doing so after a few billionths of a second. Everyday language inherited this illusion. We speak of seeing the present, looking at the world as it is, and watching events happen in real time. In physical terms, every act of vision is already an encounter with the past. The delay becomes noticeable when distance grows. We see the moon as it existed a little over 1 second ago. Sunlight reaching Earth began its outward journey more than 8 minutes earlier, after taking far longer to escape the dense interior of the sun. If the visible surface of the sun could suddenly change, Earth would continue receiving the older light throughout those 8 minutes. The sky would preserve an image of conditions that no longer existed nearby. Distance separates the event from our knowledge of the event. This separation remains modest inside the inner solar system. A few minutes feel inconvenient, though they still belong to a human scale of planning. Farther out, the delays become operational boundaries. Commands sent to robotic explorers cannot rely upon immediate correction. Each spacecraft must survive moments of danger using instructions written in advance and decisions made by its own systems. Even before humanity attempts to cross the stars, light has already imposed solitude upon every machine that travels far from Earth. Mars offers the first clear demonstration of how quickly cosmic distance overwhelms communication. Depending on the positions of Earth and Mars in their orbits, a radio message can require several minutes or more than 20 minutes to travel in one direction. A person controlling a rover cannot steer around a rock by watching a live video feed. The image of the obstacle arrives after the rover has already encountered it, and any corrective command reaches the machine after an additional delay. Exploration becomes a sequence of plans, transmissions, waiting periods, and delayed reports. A human expedition to Mars would face the same isolation. During favorable alignments, conversations with Earth would contain pauses long enough to disrupt ordinary speech. At greater separation, a single reply might arrive nearly 3/4 of an hour after the first person began speaking. Medical teams on Earth could offer advice, but the patient and local crew would handle the immediate emergency alone. Political leaders could issue instructions, yet events might develop beyond those instructions before the message arrived. Mars would remain close by astronomical standards while already existing beyond real-time human control. Beyond the orbit of Mars, the solar system expands into a realm where every exchange becomes correspondence. A message to Jupiter requires tens of minutes. Saturn lies farther still. Uranus and Neptune remain several light hours away, with the exact delay changing as planets move through their orbits. A probe near Neptune cannot report a discovery and receive guidance during the same working day in any natural conversational sense. Its controllers interact with a version of the probe preserved in old data, while the actual machine continues through an unseen future. At the outer edges explored by human spacecraft, radio signals spend much of a day crossing the darkness. The most distant probes continue transmitting extremely weak information toward Earth, and their messages describe conditions from many hours earlier. Engineers respond to a machine whose current state remains unknowable until its next transmission arrives. A fault may already have occurred. A command may reach hardware that has entered a different configuration. Every decision is directed toward an object that exists ahead of our information about it. This condition would intensify for any human colony scattered across the solar system. Communities on moons, planets, asteroids, and artificial habitats could share news and scientific data, though they could never inhabit a single immediate public conversation. A crisis near Saturn might remain unknown on Earth for more than an hour. Earth's response would arrive later, perhaps after local decisions had determined the outcome. Governments could claim authority across the solar system, but physical reality would reserve immediate authority for those present at the event. A solar civilization would therefore develop through delayed coordination. Its people could maintain common languages, institutions, markets, and cultural traditions supported by continuous communication. Each region would also acquire practical independence because distance prevents rapid intervention. The speed of light would divide political power according to travel time. Even within the small neighborhood surrounding one star, perfect unity would become impossible. The nearest star beyond the Sun lies more than 4 light-years away. That phrase can seem deceptively gentle. 4 years belongs to an ordinary interval in a human life. Children grow, governments change, buildings rise, and relationships transform during such a period. Yet the distance represented by those years approaches 40 trillion kilometers. Every kilometer must be crossed individually. The nearest stellar system stands beyond an ocean of space so large that the entire solar system shrinks into a small coastal harbor beside it. A message traveling at light speed would need more than 4 years to reach Proxima Centauri, and more than 4 additional years for a reply to return. The simplest exchange would extend across nearly a decade. A scientist on Earth might send a question early in a research project and receive the answer after changing careers. Parents could announce the birth of a child and hear the response when the child had already entered school. Elections, discoveries, illnesses, marriages, and deaths would occur during the silence between 2 lines of conversation. This delay assumes that communication can travel at light speed, that the receiving civilization is prepared to detect it, and that both sides maintain compatible technology across the entire interval. Spacecraft would move far more slowly. Voyager 1 travels fast enough to cross hundreds of millions of kilometers each year, yet a journey to the nearest star at a similar speed would require tens of thousands of years. Its destination would move during the flight. Human languages, nations, and perhaps the species itself could transform before arrival. More ambitious propulsion might reduce the voyage to centuries or decades. A craft moving at 10% of the speed of light could approach the nearest stars within a human lifetime, though accelerating a large vessel to such a speed would require enormous energy. Dust grains would strike with destructive force. Radiation would intensify. Deceleration at the destination would demand another vast expenditure. A journey that appears brief on a cosmic diagram would become one of the greatest engineering projects a civilization could attempt. Even after reaching another star, the settlers would remain tied to Earth through a thread measured in years. News would arrive in historical blocks. A colony could report a crop failure, receive advice almost a decade later, and discover that the specialists who wrote the answer had never witnessed the colony's eventual recovery. Military aid, emergency supplies, and direct governance would arrive too late to solve sudden problems. Interstellar settlement would create societies connected by ancestry and information, though separated by causality. The nearest stars tempt us because they appear clustered around the sun on maps. Cosmic maps compress distance until systems separated by trillions of kilometers become neighboring dots. In physical space, each gap carries years of darkness. The first interstellar community would discover that light permits contact while refusing intimacy. The stars remain visible to one another, but their lives unfold in different times. The Milky Way contains hundreds of billions of stars distributed across a disk roughly 100,000 light-years wide. Our solar system occupies a region far from the galactic center, embedded within one part of a spiral structure that curves through the surrounding darkness. From Earth, the galaxy appears as a pale river across the night sky. That soft band conceals a territory whose dimensions make the nearest star problem seem almost local. A beam sent toward the galactic center needs tens of thousands of years to arrive. Human beings were still living in the Stone Age when the light currently reaching us from that region began its journey. A message sent today would reach the center after every present nation, language, and institution had probably disappeared or changed beyond recognition. The response would return after another interval comparable to the entire span of recorded civilization many times over. Crossing the full galactic disk at light speed requires about 100,000 years. A civilization located on the opposite side of the Milky Way could transmit continuously throughout its entire history without receiving any indication that humanity had developed technology. Our earliest radio leakage has traveled only a tiny distance compared with the diameter of the galaxy. Most of the Milky Way remains outside the expanding sphere of signals produced by modern Earth. This scale changes the meaning of a galactic civilization. Science fiction often imagines an empire whose capital communicates with distant worlds, coordinates fleets, announces laws, and responds to rebellion. Such a system would face delays measured in centuries or millennia. An order from the center might reach a frontier after the government that issued it had collapsed. A tax request could arrive after the colony had developed a different economy. A fleet sent to restore authority might encounter a society whose founding dispute survived only in historical archives. Galactic unity could exist through shared principles rather than immediate administration. Each region might receive cultural archives, scientific discoveries, and legal traditions from distant neighbors. Local societies would interpret these materials according to conditions unknown to the sender. A constitution could spread across the stars like a slow biological inheritance, changing during every transmission. The galaxy might support a family of civilizations whose common origin remained visible while no central observer knew their present condition. Any map of such a civilization would already be obsolete. A telescope aimed at a settlement 10,000 light-years away shows the settlement 10,000 years in the past. Its present population, architecture, and perhaps its star remain concealed. Messages sent toward the visible world would address descendants who had never known the people in the image. Galactic geography would combine distance with historical depth, turning every direction into a different age. Suppose an advanced civilization learned to send ships at nearly the speed of light. The nearest stars could be reached within years from the perspective of Earth, and more distant regions within centuries or millennia. Expansion through the Milky Way might proceed through waves of settlement. Each colony could launch new missions toward nearby systems, allowing life to spread without requiring any single vessel to cross the entire galaxy. Even under favorable assumptions, the resulting civilization would fragment through delay. Colonies founded a few light years apart could exchange messages across manageable intervals. As the settlement wave expanded, the oldest and newest regions would drift beyond meaningful conversation. The founding planet might receive information about communities established thousands of years earlier while remaining ignorant of everything that followed. Those communities would know Earth through messages equally ancient. Cultural evolution would amplify the separation. Language changes over centuries. Political institutions respond to local crises. Biology might adapt to different gravity, atmosphere, radiation, and available resources. Artificial intelligence and genetic engineering could accelerate divergence. By the time a message completed a journey across the galaxy, sender and receiver might share little beyond historical ancestry and the basic laws of physics. A traveler moving close to light speed would experience time differently. Relativistic time dilation could allow a crew to cross enormous distances while aging less than people who remained behind. From their perspective, a voyage across part of the galaxy might fit within a lifetime if they traveled sufficiently close to the limit. Outside the ship, thousands or tens of thousands of years would pass. Arrival would bring them into contact with the future created during their absence. This possibility turns high-speed travel into a form of one-way migration through time. Returning to the place of departure would rarely restore the life left behind. Friends, descendants, institutions, and familiar cultures would belong to the remote past. The travelers could reduce their own experience of distance while remaining unable to reduce the time elapsed for the galaxy around them. Relativity grants access to distant places at the price of separation from the original era. A civilization using such travel might contain wandering populations who leap across centuries. A crew could depart from one world, spend several subjective years in flight, and arrive after entire civilizations had risen and fallen. They would carry information from a past nobody else remembered directly. Each ship would function as a vessel, archive, and fragment of another age. Light speed would remain unreachable, and approaching it would transform the meaning of travel long before the limit itself came into view. The Milky Way belongs to a collection of galaxies known as the Local Group. Andromeda, the largest neighboring spiral galaxy, lies roughly 2.5 million light-years away. The light visible through telescopes began traveling toward us when early members of the human lineage were living on Earth. We see Andromeda before cities, writing, agriculture, and modern humanity shaped the planet. Its current state will remain hidden for another 2.5 million years. A message sent toward Andromeda today would arrive after a duration longer than the entire existence of our species so far. Any reply would return millions of years later. Continents would move. Species would emerge and disappear. The sun itself would be measurably older. The concept of conversation loses coherence across such a distance. The sender can have no realistic expectation that the receiving society will resemble the one first observed. Travel would be more severe. Even a vessel moving at a remarkable fraction of light speed would spend millions of years between the galaxies from the perspective of those left behind. Generations could live and die aboard, unless suspended animation or radical life extension changed human biology. Mechanical systems would need to survive periods exceeding the age of many species. The slightest long-term failure rate would accumulate across an almost incomprehensible duration. Andromeda appears close when compared with the wider universe. The local group extends across millions of light years and contains many smaller galaxies bound together by gravity. Beyond it, galaxies form groups, clusters, filaments, walls, and vast empty regions. The cosmic web stretches across hundreds of millions and billions of light years. Each increase in scale diminishes the practical meaning of light speed. A civilization distributed across the local group would never possess a shared present. Its regions could exchange information, though every message would function as a contribution to deep history. A culture in Andromeda might receive records from the Milky Way describing life before a geological transformation that had already erased the senders. The reply could be addressed to a planet whose oceans had changed and whose inhabitants belonged to a different branch of evolution. The two great spiral galaxies are moving toward an eventual encounter under their mutual gravity, though the process unfolds over billions of years. Stars will follow altered paths as the galaxies merge into a new structure. Any civilization lasting long enough to observe that transformation would think in intervals far beyond recorded human history. Yet even for such beings, light would require millions of years to carry information from one side of the merging system to the other. The observable universe has a radius of about 46 billion light-years when distance is measured according to the present cosmic arrangement. This can appear contradictory because the universe is around 13.8 billion years old. Light has not spent 46 billion years traveling toward us. Space expanded while the light was in transit, increasing the present distance between Earth and the regions that emitted the oldest observable radiation. The farthest light we can detect comes from an early period when the universe became transparent. Before that time, matter existed as a hot plasma that repeatedly scattered photons. Once atoms formed, radiation could travel freely across space. That ancient light has been stretched by cosmic expansion into microwave wavelengths. It now surrounds us as a faint background arriving from every direction, carrying an image of a universe only hundreds of thousands of years old. The matter that emitted this radiation occupies regions now vastly farther away than the simple product of light speed and cosmic age would suggest. We observe its ancient condition while calculating its present distance through models of expansion. The visible edge of the universe therefore resembles a historical surface. Looking outward means looking backward, and greater distance reveals earlier stages of cosmic development. A galaxy seen 10 billion light-years into the past may have transformed, merged, or ceased producing stars long before its image reached Earth. Its light gives real information, though the information belongs to an unreachable chapter of its history. Astronomers reconstruct cosmic evolution by assembling these delayed views. Telescopes act as instruments of time, collecting photons that departed before the solar system existed. The observable universe contains no single image of the present. Nearby objects appear comparatively recent. Distant galaxies appear young. The cosmic background reveals an era before galaxies had fully formed. Every astronomical survey combines different times into one apparent sky. The darkness above us resembles a layered archive whose pages arrive together despite having been written across billions of years. No observer can see the whole universe as it exists at one universal instant. Relativity itself complicates the idea of a shared cosmic present, while the finite speed of information ensures that distant conditions remain inaccessible. Even an ideal telescope cannot reveal what is happening now on the far side of the observable universe. The photons carrying that information may not reach our region for billions of years, and cosmic expansion may prevent some from arriving at all. Cosmic expansion creates distances whose behavior differs from ordinary motion. Galaxies separate because the large-scale geometry of space changes over time. Nearby gravitationally bound systems resist this expansion. Earth remains bound to the Sun, stars remain bound within the Milky Way, and the galaxies of the local group remain tied by their mutual gravity. Across immense scales, however, the average distance between unbound galaxies increases. A sufficiently distant galaxy can recede from us at an effective rate greater than the speed of light because the intervening space expands. This does not involve the galaxy moving locally through space faster than light. Relativity restricts the local motion of matter and information. It does not impose the same simple limit upon the growth of distance created by the expansion of space-time itself. Light emitted by a receding galaxy may initially find the distance to Earth increasing even while the photon travels toward us locally. As cosmic conditions change, the photon can later enter a region where it makes net progress and eventually reaches our telescopes. This is one reason intuitive pictures of light-chasing galaxies through static space produce confusion. The geometry through which the light moves evolves during the journey. The universe also appears to be undergoing accelerated expansion. Dark energy is the name given to the unknown cause associated with this behavior. If the acceleration continues in a form resembling current models, increasingly distant galaxies will pass beyond a cosmological event horizon. Light they emit after a certain time will never reach us, regardless of how long future observers wait. This horizon defines a profound boundary. Regions beyond it may continue to exist, form stars, host planets, and undergo entire histories. No message sent from Earth in the future could reach some of them. No event occurring there sufficiently late could influence us. The separation would arise from the structure of space-time, leaving no wall, edge, or visible marker. The observable universe contains many galaxies whose ancient light reaches us today, even though signals sent now could never reach their present locations. We can see their past while remaining causally separated from their future. The image enters our telescopes like a final letter from a shore that has already moved beyond every possible journey. Light reveals the universe and simultaneously demonstrates how much of it is slipping away. The speed of light is tied to the structure of space and time through special relativity. An object with mass requires energy to accelerate. As its velocity approaches the speed of light, the energy required for further acceleration grows dramatically. Reaching the limit would demand an infinite amount of energy according to the theory, placing light speed beyond the reach of any massive spacecraft, human body, dust grain, or atom. Photons travel at this limit because they possess no rest mass. The relationship between space and time along a light-like path differs from the experience of ordinary matter. Popular explanations sometimes imagine the journey from the perspective of a photon and claim that no time passes for it. Physics does not provide a valid resting frame for light, so a photon cannot be assigned an ordinary viewpoint. Its path still marks the boundary between events that can influence one another and events that remain causally separated. Relativity also means that observers moving differently can disagree about distances, durations, and whether separated events occur simultaneously. They continue to agree upon the speed of light. A beam measured from a stationary laboratory moves at the same speed as a beam measured from a spacecraft racing in the same direction. Velocities do not combine through the simple arithmetic familiar from slow motion. This feature protects causality. If information could move arbitrarily faster than light, different observers could arrange the order of certain events differently. Under some circumstances, a message could be received before it was sent according to another reference frame. Faster than light communication would open paths toward contradictions involving cause and effect. The cosmic speed limit helps maintain the consistency of physical history. The limit also gives every event a light cone. The future light cone contains locations that a signal traveling at or below light speed could influence. The past light cone contains events capable of influencing the present. Everything outside these cones remains separated by space-time intervals that no ordinary signal can cross. Each person moves through reality surrounded by these causal boundaries. On Earth, light cones from nearby events overlap quickly, creating the impression of a shared present. Across interstellar distance, the overlap develops slowly. Across cosmological distance, expansion can prevent it from developing at all. The universe contains regions whose histories may remain permanently independent, even though they belong to the same cosmos and obey the same physical laws. Near light speed travel offers extraordinary possibilities. Though its practical demands become brutal, the energy of a spacecraft increases enormously as it approaches the limit. Accelerating a modest payload to a significant fraction of light speed would require energy comparable to the output of large human industries. A crewed vessel with shielding, life support, fuel, engines, and supplies would multiply the challenge. Acceleration represents only half the journey. A craft intended to stop at its destination must remove nearly all the kinetic energy acquired during departure. Carrying fuel for both stages increases mass, which demands more energy, which can require additional fuel. Propulsion designs attempt to escape this cycle through external beams, antimatter, fusion, magnetic sails, or other concepts. Each approach faces limits involving efficiency, heat, materials, infrastructure, and control. Interstellar space also contains gas and dust. At ordinary spacecraft speeds, tiny particles present manageable hazards. At a large fraction of light speed, a collision with a grain can release enormous energy. Individual atoms strike the vessel like intense radiation. The front of the ship requires shielding capable of surviving a continuous stream of high-energy impacts without becoming dangerously hot or gradually eroding. Navigation becomes severe because the craft covers immense distances during the time required to detect and respond to danger. A small object observed too late could be impossible to avoid. Active protection might use forward sensors, sacrificial shields, magnetic fields, or material projected ahead of the vessel. Every protective system adds mass and complexity. Human bodies introduce further constraints. Acceleration must remain tolerable, living conditions must continue for years or decades, and radiation exposure must remain controlled. A ship accelerating continuously at a comfortable rate could reach relativistic speeds, though sustaining such acceleration requires an energy source far beyond present capability. Engine failure at high speed could leave the crew moving through interstellar space with limited options for repair or rescue. The speed of light therefore acts as a distant ceiling above a landscape of practical ceilings. Engineering becomes punishing long before the theoretical limit is approached. Reaching 1% of light speed would already represent an extraordinary achievement for a large spacecraft. 10% would transform interstellar travel. 90% would demand capabilities separated from modern technology by an uncertain gulf. Communication may become easier than travel because information can be carried by light itself. A civilization could send radio waves, lasers, or tightly focused beams between stars without accelerating a massive vehicle. The signal still suffers from delay, weakening, interference, and the difficulty of aiming at a moving target across years of travel. A laser directed toward another star spreads with distance, even when the beam is extremely narrow. The receiving civilization must possess a sufficiently large and sensitive detector, know where and when to observe, and distinguish the signal from natural radiation. Powerful transmitters and large telescopes could make interstellar communication possible. They cannot make it immediate. Messages would likely become self-contained packages. A transmission to a distant colony could include scientific data, cultural works, software, medical discoveries, engineering designs, and personal recordings. The sender could provide context for recipients living decades or centuries later. Questions would be written with the understanding that answers belonged to another stage of history. Artificial intelligence might represent distant communities in the interval. A colony could maintain a model trained on Earth's archives and recent transmissions, allowing inhabitants to consult a simulation of institutions that existed years earlier. Earth could maintain similar models of the colony. These systems would create continuity, though they could never reveal events whose signals had not arrived. At greater distances, communication becomes inheritance. A civilization could transmit knowledge toward worlds that would receive it after the senders had vanished. The message might contain instructions for decoding language, mathematics, biology, and history. Recipients would encounter a cultural fossil capable of speaking. Any reply would travel toward an uncertain future. The galaxy could fill with such messages. Beams might cross one another between stars, carrying extinct languages and forgotten political disputes. Some would reach planets without technology. Others would pass through systems whose inhabitants had moved elsewhere. A few might be detected after traveling for thousands of years, providing evidence that intelligence once existed around a star now quiet. Light allows information to survive its creators. Its finite speed turns that survival into delay. The message remains alive in transit while every society at its origin continues to change. By the time it arrives, it may represent a civilization that no longer recognizes itself. The search for extraterrestrial intelligence takes place inside this ocean of delayed information. When astronomers examine a planet hundreds of light years away, they see conditions from hundreds of years earlier. A sign of technology would reveal that a civilization existed when the light departed. Its present survival would remain unknown. Earth's own technological signals have expanded outward for little more than a century. The resulting sphere covers a tiny region of the Milky Way. Many nearby stars have received no evidence of modern humanity. Civilizations elsewhere could be looking toward the solar system and seeing Earth before radio, industry, cities, or even complex animals, depending upon their distance. This makes apparent silence difficult to interpret. A technological species may exist beyond the reach of its signals. A society might have transmitted during an era whose radiation has not reached Earth. Another could have vanished before humanity developed the ability to listen. Two civilizations can occupy the same galaxy for millions of years without their communicative periods overlapping in the correct way. Signals also weaken and change. Ordinary radio leakage may become undetectable across interstellar distance. Advanced societies could use efficient communication methods that produce little accidental radiation. They might direct beams toward known recipients rather than broadcasting into the galaxy. Silence can result from distance, timing, technology, caution, or absence. The speed of light expands the number of missed encounters. Imagine two civilizations separated by 10,000 light years. One transmits for 500 years and disappears. The other begins listening 1,000 years after the final signal has already passed its planet. Their periods of technological existence overlap across the galaxy, though neither becomes aware of the other. Cosmic history contains both of them without creating a meeting. Even a successful detection would begin a relationship stretched across geological time. A reply to a signal from the opposite side of the Milky Way could require tens of thousands of years. Humanity might answer because the act carries meaning, knowing that the intended recipients could be gone. Communication would resemble the construction of a monument sent into time rather than a conversation. The universe may contain abundant intelligence and remain emotionally silent. Light is fast enough to reveal that stars exist. It may be too slow to bring their living moments together. Astronomical observation depends upon this same delay. When a star explodes, telescopes on Earth detect the event after its light has crossed the intervening distance. The explosion could have occurred centuries, thousands of years, or millions of years earlier. Astronomers say that the event is being observed now, meaning that its influence is reaching Earth now. The source itself belongs to another time. A nearby stellar explosion could already have occurred without our knowledge. The star would continue appearing unchanged until the first radiation arrived. No telescope could reveal the event early through ordinary observation because any warning signal would travel no faster than the light of the explosion. Neutrinos or gravitational waves might arrive slightly earlier under particular physical conditions, though they still obey the same fundamental causal limit. This creates an astronomy filled with delayed catastrophes. Galaxies collide in images assembled from ancient photons. Black holes merge long before their gravitational waves reach detectors. Stars form inside nebula clouds, whose current shapes may differ from everything visible. We study real events through evidence that has spent enormous periods traveling toward us. Prediction becomes local and probabilistic. Astronomers can understand stellar evolution, estimate lifetimes, and identify unstable systems. They cannot inspect the present condition of a distant object without waiting for its current light. A star 1,000 light years away exists 1,000 years beyond the latest information available to Earth. The same applies to planets. A world observed with atmospheric signs associated with life displays an earlier biosphere. By the time humanity sends a probe or message, the planet may have changed. Climate, geology, evolution, and civilization continue during every year of transit. Exploration targets historical versions of worlds and arrives at futures that were invisible when the mission began. Every photograph of deep space therefore contains an element of uncertainty. The universe depicted in the image has never existed as one simultaneous arrangement. Each region contributes light from a different era. The picture resembles a mosaic made from moments separated by billions of years, presented together because their photons happen to reach the detector during the same exposure. The slowness of light becomes even more striking near black holes. Gravity bends space-time, altering the paths followed by radiation. Light can orbit a black hole along unstable trajectories near a region known as the photon sphere. A small disturbance sends it inward or outward. Closer still lies the event horizon, beyond which no future-directed path leads back to the external universe. To a distant observer, matter falling toward the horizon appears increasingly slowed and redshifted. Its emitted light loses energy and arrives over longer intervals until the object fades from view. From the falling object's own experience, crossing can occur within a finite amount of proper time, assuming the black hole is sufficiently large and other forces remain survivable. Inside the horizon, the inability to escape involves the causal structure of spacetime. Every possible future path points deeper inward. Light remains locally fast, always traveling at the universal limit, yet no direction leads outward toward distant observers. The fastest messenger in nature cannot overcome the geometry surrounding it. Black holes therefore reveal that speed alone does not guarantee access. Light can move at its absolute limit and remain trapped. Across cosmology, expansion creates another form of inaccessibility. In both cases, space-time determines which destinations belong to the future of a signal. Information near black holes raises some of the deepest questions in theoretical physics. Quantum mechanics and gravity must somehow account for what happens to information associated with matter crossing the horizon. Proposed resolutions involve subtle relationships among radiation, entropy, geometry, and quantum states. The problem demonstrates how closely light, causality, and the structure of reality are connected. From the scale of a black hole to the scale of the universe, horizons divide what can influence us from what cannot. They carry no material wall. An observer may cross a horizon without encountering a visible boundary at that instant. The separation appears in the future paths available to light. Human beings often imagine overcoming the limit through wormholes. General relativity allows mathematical geometries in which distant regions connect through a shorter path. A traveler entering one mouth might emerge far away without locally exceeding light speed. The route could make the effective journey appear faster than a beam traveling through ordinary space. Whether traversable wormholes can exist remains unknown. Many models require forms of negative energy or unusual stress capable of holding the passage open. Quantum theory permits limited negative energy effects under certain conditions, though scaling them into a stable structure large enough for travel presents immense difficulties. Wormholes may collapse, become unstable, or remain forbidden by physical principles not yet fully understood. Warp drive concepts use another geometric idea. A region surrounding a spacecraft could contract space ahead and expand it behind, carrying the vessel while it remains locally at rest inside the distorted geometry. The original mathematical proposal required extreme and exotic energy distributions. Later work has explored variations, though no known method can build, control, or power such a structure. These ideas also face causal problems. Arrangements allowing effective faster-than-light travel can often be transformed into paths resembling travel into the past. Chronology violations and paradoxes appear. Some physicists suspect that deeper laws prevent the formation of usable time machines, perhaps through quantum effects that become destructive as causality is threatened. Speculation remains scientifically valuable when it clarifies the limits of known theory. Wormholes and warp geometries reveal that general relativity permits surprising structures. They also show how much separates a valid equation from a physical technology. A solution can demand matter that may not exist, energy beyond any accessible source, or initial conditions that no civilization can arrange. Future discoveries could alter our understanding of space-time. History contains many technologies that earlier generations could not imagine. The speed of light occupies a deeper role than the limits overcome by faster ships, aircraft, or computers. Surpassing it would require changing how distance, causality, and time operate. The obstacle belongs to the framework within which every technology functions. Even a civilization unable to move faster than light could transform itself to accommodate cosmic distance. Biological life could be extended, suspended, copied, or replaced by durable machines. Minds might travel as information encoded within probes. A small automated craft could carry genetic material and manufacturing systems toward another star, constructing habitats before biological settlers arrived. Digital minds could slow their subjective experience during long voyages. A system might remain dormant for centuries, awakening periodically to inspect the spacecraft. For its inhabitants, an interstellar crossing could feel brief even though the external universe aged normally. This would solve the problem of patience without changing the speed of travel. Civilizations could also spread through self-replicating probes. Each machine would reach a system, use local materials to create copies, and send them onward. The expansion front could cross the galaxy within millions of years, a short interval compared with the age of the Milky Way. The network behind that front would still suffer from communication delays, cultural divergence, and uncertain control. Copies of the same mind could depart toward different stars. After years of separate experience, they would become distinct individuals. When messages finally arrived, each version would encounter a delayed relative shaped by another history. Identity would fragment across light years in ways human law and psychology have never addressed. A civilization might accept that coordination across the galaxy is impossible and design its expansion accordingly. Every settlement could receive principles, knowledge, and tools for independent survival. The goal would center upon diversity and continuation rather than obedience to an origin. Light-speed delay would become part of the architecture of civilization. Such a culture could resemble biological evolution. Information spreads, changes, branches, and adapts. Some branches disappear. Others become unrecognizable. No central authority controls the entire process. The galaxy fills gradually with related forms of life whose common ancestry lies buried beneath millions of years of separation. The speed of light would remain too slow for unity while proving sufficient for inheritance. A civilization could seed the stars without ever seeing the final result. The future universe may make the problem more severe. If accelerated expansion continues, galaxies beyond the local group will gradually recede from view. Their light will become increasingly redshifted, stretched toward longer wavelengths and lower energies. Star formation will decline. Distant structures will cross the event horizon, leaving no new signals capable of reaching us. Future observers living hundreds of billions or trillions of years from now could inhabit a universe that appears far emptier. The Milky Way and Andromeda will have merged into a larger gravitationally bound galaxy. Other members of the local group will remain nearby. The wider cosmic web may have disappeared from observable reach. Those observers could possess incomplete evidence for cosmic expansion and the early universe. Ancient records might tell them that billions of galaxies once filled the visible sky. Direct observation could become difficult or impossible as the relevant light faded beyond detection. Cosmology would depend upon archaeology, preserved data, and confidence in ancestors who witnessed a richer cosmos. Light would have lost the race against expansion. Photons from distant galaxies would continue traveling locally at the universal limit, yet the growing geometry between regions would prevent new information from arriving. The visible universe would contract in practical terms until the local galactic remnant appeared alone within darkness. This fate gives the present era a special quality. Humanity can observe the cosmic background, measure expansion, map the large-scale distribution of galaxies, and study light spanning most of cosmic history. The universe has become old enough for complex observers while remaining young enough for distant structures to remain visible. Every telescope gathers evidence that future time may erase from access. Astronomy preserves a universe already beginning to disappear. Light carries the record toward us, though the record becomes fainter, redder, and older with every passing age. There is a quiet cruelty in the relationship between light and distance. The universe allows us to see places that we may never reach. It presents galaxies in exquisite detail while locating them millions or billions of years away. Their photons enter human eyes, strike detectors, and become images inside our minds. Physical contact remains beyond any plausible journey. Vision creates emotional proximity. A photograph of a distant nebula cloud can appear immediate enough to touch. Colors and structures fit within a screen held in one hand. The image compresses scale and hides travel time. It makes a region thousands of light years wide seem present within the room. The true object may already have changed. Its stars move, gas disperses, new systems form, and old systems vanish. We receive one chapter carried across space while later chapters remain on their way. The universe surrounds us with appearances whose sources have continued into unknown futures. Human history occurs within a tiny causal neighborhood. Most events that will influence our lives originate on Earth, around the Sun, or within a modest astronomical distance. The greater universe shapes our origins, elements, gravity, and long-term fate while remaining largely absent from daily cause and effect. This separation can make the cosmos feel like scenery. Galaxies decorate the night without participating in ordinary life, yet their distance carries physical meaning. It determines what can know what, who can answer whom, and whether two histories can ever meet. The speed of light is immense enough to build the visible universe. It carries the radiation of stars, the signatures of planets, the echoes of the early cosmos, and the gravitational tremors of colliding black holes. Its apparent slowness emerges from the extraordinary dimensions it must cross. The universe has made its fastest messenger responsible for distances almost beyond measure. Imagine a signal leaving Earth tonight. It rises through the atmosphere, crosses the orbit of the moon, and passes the planets one by one. Within hours, it has traveled farther than any human being. After a year, it has crossed nearly 10 trillion kilometers. The Sun has become another star behind it. 4 years later, the signal reaches the nearest stellar systems. Decades pass as it moves through the local neighborhood. Human lives begin and end on Earth. Cities change. Languages acquire new words. The transmission continues outward without aging, its encoded message preserving the moment of departure. After a century, it has reached only a small collection of nearby stars. The Milky Way remains almost entirely ahead. After 1,000 years, it has crossed a region that still appears tiny on a galactic map. Humanity may have transformed or vanished while the signal continues announcing a world from the early 21st century. Tens of thousands of years later, it approaches distant parts of the galactic disk. Any receiver hears a voice from an age more remote than the earliest human cities are to us. The message describes people who hoped that someone might be listening. A reply begins its return, though Earth will wait another tens of thousands of years. The signal could eventually leave the Milky Way and travel through intergalactic darkness. Millions of years pass. Galaxies evolve, stars exhaust their fuel, planetary systems scatter. The message survives if its beam remains coherent and a detector happens to lie along its path. Across these distances, light seems slow because history moves while it travels. The messenger never pauses. The worlds at either end simply change too quickly compared with the journey. A universal speed limit gives the cosmos a structure that an instantaneous universe would lack. If information could appear everywhere at once, distance would lose much of its meaning. Every event could influence every other event immediately. The universe would possess a single connected present, exposed simultaneously to all observers. Instead, reality unfolds locally. Causes spread outward at finite speed. Stars form without the distant universe knowing immediately. Planets develop for billions of years beyond the awareness of neighboring systems. Life can emerge inside pockets of causality whose existence remains hidden elsewhere. This locality may be essential to complexity. Systems can develop with limited interference from distant events. Regions preserve their own histories. Information arrives gradually, allowing structures to respond through chains of cause and effect. The universe becomes a tapestry woven from overlapping horizons rather than one perfectly synchronized machine. For human beings, this structure creates freedom and isolation together. No distant civilization can intervene in Earth's immediate choices. No galactic authority can arrive tomorrow. Our future depends overwhelmingly upon decisions made within our own causal neighborhood. It also means that discovery carries responsibility. A signal detected from another star would represent a voice that traveled alone through years of darkness. An image of a distant planet would reveal a world unable to know that it had entered human thought until a message reached it much later. Astronomy receives information without granting immediate reciprocity. The speed of light defines the rhythm of cosmic relationship. Every connection requires time. Every answer comes from a future the sender cannot predict. Every journey transforms the traveler's bond with home. The universe may extend far beyond the observable region. It could be finite on an enormous scale or spatially infinite. Current observations cannot reveal the whole because information from sufficiently distant regions has had no time to reach us. The boundary of observation marks a horizon in knowledge rather than a physical edge. Beyond that horizon, space may contain more galaxies, stars, planets, and forms of matter arranged under the same laws. There could be regions so distant that no signal from them will ever enter our causal future. Their events remain part of reality while remaining absent from every possible human observation. This creates a limit deeper than technological ignorance. Better telescopes can reveal fainter and earlier light within the observable universe. No detector can receive a signal that space-time never permits to arrive. Some truths may remain permanently outside every experiment conducted in our region. The scale of the unknown therefore exceeds the scale of darkness visible through telescopes. Darkness can contain objects whose light is too faint, too redshifted, blocked, or simply still traveling. Beyond the cosmological horizon lies a more absolute absence of information. We cannot distinguish empty space from an unobservable abundance through direct evidence. A civilization surviving for trillions of years might learn almost everything available within its causal region. It could map every accessible system, preserve the histories of countless stars, and understand physical law with extraordinary depth. The wider universe could remain hidden. Intelligence would confront the same boundary faced by every photon. Knowledge spreads through causal paths. Where those paths cannot reach, curiosity encounters silence. Perhaps the deepest consequence of light's finite speed lies in the impossibility of a universal witness. No observer can occupy every place or receive every event as it occurs. The universe possesses no accessible balcony from which its whole present can be seen. Every viewpoint remains embedded within space-time, receiving one limited arrangement of delayed information. Earth sees the cosmos from one location and one era. A civilization in another galaxy would see a different observable universe centered upon itself. Its cosmic horizon would include regions unavailable to us and exclude regions we can observe. Neither perspective would hold the complete history. As civilizations move and time passes, their accessible regions change. Some information enters view. Other information crosses horizons and disappears. Knowledge belongs partly to location. A perfect archive created elsewhere may remain unreachable because no signal can bridge the separation. This gives cosmic history an unusual fragility. Events can occur magnificently, shape vast regions, and leave no trace capable of reaching us. Entire civilizations could exist beyond our horizon without ever sharing a causal chain with Earth. Their joy, suffering, discoveries, and extinction would remain real while forever absent from human knowledge. The universe therefore exceeds its own visibility. Reality contains more than any observer can gather, and the speed of light enforces that difference. Our maps represent the part of existence that has had time to speak to us. The sun will continue sending light outward long after every person alive today has disappeared. Some photons leaving its surface now will pass planets, cross the outer solar system, and enter the space between stars. They may travel through the Milky Way for thousands of years without striking anything. Others will be absorbed by dust, planets, or distant instruments. The light reflected from Earth also escapes. It carries faint images of oceans, clouds, continents, and city lights into the galaxy. At increasing distance, the planet becomes too small and dim to resolve. In principle, information about this moment continues moving outward, spread across an ever-growing sphere. A sufficiently advanced observer positioned at the correct distance could see Earth's past. From 100 light-years away, the planet appears as it was a century earlier. From several thousand light-years away, its light reveals an age before recorded history. The past remains physically present as radiation traveling through space, though recovering detailed images would demand impossible or extraordinary instruments. There is something haunting in this expansion of old moments. Childhood homes, vanished landscapes, and people long dead have reflected photons that still move through the universe. Most will never be collected into an image. They carry traces without a witness. Light preserves and loses at the same time. It allows events to influence distant places while diluting their detail across enormous areas. The universe becomes filled with fading evidence of everything that has happened, traveling outward until absorption or expansion renders it inaccessible. Our present will eventually become part of that faint archive. The fastest messenger nature permits will carry it through the dark, slowly crossing a universe far larger than any single moment can reach. Light feels slow because the human mind can imagine destinations more easily than it can inhabit the distance between them. We see a star, give it a name, and place it on a map. Thought arrives immediately. Physics demands years. We photograph a galaxy and hold it within a frame. Imagination crosses its spiral arms in seconds. Light needs tens of thousands of years. The apparent closeness created by knowledge conceals the separation imposed by space-time. No engine can currently approach the universal limit. No message can exceed it. No telescope can show the distant present. Every attempt to explore the cosmos begins beneath the same restriction. Yet the slowness of light also gives depth to the sky. Each star becomes a memory. Each galaxy opens a different period of history. Looking outward transforms distance into time, allowing one world to observe billions of years of cosmic evolution. The night sky would be poorer if light arrived instantaneously. We would see a single present whose distant parts might already be old, dark, or inaccessible. Finite travel time turns the universe into an archive visible from within itself. The price of that archive is separation. We can witness the infancy of galaxies while remaining unable to discover their current fate. We can search for distant life while knowing that any answer may outlive the species that asked the question. One day, humanity may send a vessel toward another star. Its engines will burn against the silence, raising its speed far beyond anything achieved before. Earth will diminish behind it. Messages will continue crossing the widening interval, arriving later with every stage of the journey. The crew may watch recordings of a home that has already changed. Their families will age between transmissions. News will become history before reaching the ship. At the destination, they may step into another system carrying memories of an Earth that no longer exists in the same form. They will have crossed only a few light years. The galaxy will still extend tens of thousands of light years in every direction. Andromeda will remain millions of years away. The distant universe will continue receding beyond every practical journey. That first voyage may feel heroic because the distance is so severe. It may also reveal how small our reach remains. A path that consumes generations appears invisible against the scale of the Milky Way. The explorers will understand the universe through a truth impossible to feel from Earth. Space is filled with destinations and almost empty of arrival. Light crosses the void with perfect endurance, though even light spends years, ages, and epochs on the road. The speed of light is often described as the fastest possible speed. The description is correct, though it hides the greater story. Speed matters only in relation to distance, and the universe has created distances capable of making the maximum feel inadequate. Across a room, light is instantaneous to human perception. Across the solar system, it introduces delay. Across the stars, it separates generations. Across the galaxy, it separates civilizations. Across the observable universe, it separates entire eras of cosmic history. No increase in patience can overcome every horizon. Some messages have not arrived. Some will arrive after their sources disappear. Others will never arrive under the future expansion of space-time. The cosmos can therefore contain countless events without producing a shared present. It can contain observers who see one another only as ancient images. It can contain worlds close enough to appear in the same sky and distant enough to remain strangers forever. Light reveals the scale of existence by failing to cross it quickly. Every delayed photon measures the depth of space. Every old image reminds us that the universe exceeds the reach of immediacy. The stars seem near because their light has completed the journey. The journey itself remains hidden inside the brightness. Beyond each visible point lies a distance filled with years. Beyond the nearest stars lies a galaxy filled with millennia. Beyond the galaxy lies a universe filled with ages, expansion, and horizons. Light never slows. The universe is simply too large.